Hi guys, good evening everyone. Very good evening everyone. Welcome to the session and welcome once again to some previous year questions discussion. So this is the session where we are discussing the previous year questions. Just a second. Okay, yeah. So we are discussing the previous year questions of control systems for the past 3 years. It is good to know the recent trends happening, what is the recent level of exam and what are the areas they are focusing more. So previous year questions 2021, 22, 23 for control system, and this is the questions of EE branch. Okay, just Monday we discussed the question of, Tuesday we discussed the question of EC, but okay, I have divided into branch wise so that you get the collections of EC and EE questions separately, but at the same time it is a common subject. Whatever your branch may be it EC or EE, you should attempt, you should watch both the sessions, EE also, EC also, you get more variety of practice. And even if your branch may be IN also, then also this session can help you, right? Very good evening, Rohit. Chalo ji, so let's get started guys. Let's get quickly moving ahead. Is a regular introduction. Okay, so I'll share you my Telegram link in the chat box also sometime, so you can get the today's PDF class along with complete solution for other doubt discussions, for other upcoming exam notification, PSU vacancy and etc. Just be updated about everything that is happening around GATE. Okay, you can be connected in my Telegram group. So coming to the first question guys, quickly, here it is. Okay, for the closed loop system shown, what is the transfer function E by R? It's a very direct question. Okay, the error function, we know that error function is R upon 1 plus GH. Okay, so E by R is 1 upon 1 plus GH, R upon 1 plus GH. So E by R is 1 upon 1 plus GH. In case if you forget, you can just calculate this. So here error function has been defined for non-unity also, no problem. They have defined this as the error function. You have to calculate the transfer function. Forget it is error or what, you have to calculate the transfer function. Okay, and what it is going to be? So see, okay, the signal at this node C is given by EG. Okay, signal is given by EG. Now what is the value of E? Okay, the output of the summing point, that is R minus CH. This is C multiplied by the gain H. So R minus CH, I will substitute the value of C. Okay, that is EG. So it becomes EGH. E on the left side, 1 plus GH equal to R. So here you have E by R, the transfer function is 1 upon 1 plus GH. A very fundamental one, option number C. This can be directly also known to you. Okay, G. So option number C. Let's move ahead to the next case. 2023, that was 2021. 2023 EE 1 mark simple question from block diagram again. The block diagram shown in the figure, find the transfer function. You can apply BDR rules, you can convert to SFG, but I have told you several times in my earlier classes also, if it is block diagram and especially 1 mark, try to observe the block diagram. Maybe by just writing a one-line equation, you get your answer. Okay, no need to use any BDR technique, no need to use any Mason's gain formula. Okay, right. Good evening, Chinmay. Okay, Pushpraj, so then you need to first take admission into engineering to learn all of these concepts. Okay, so now this is the input R multiplied by 2. That's what I'm telling. We can make this really simple without using any BDR technique. Okay, here it is going to reach us 3R, or 3R, correct? Now, what is the output of this summing point? See, one of the input is 2R, okay, plus Y. Okay, Y goes to this block, the gain is simply 1. So what comes here is only Y. Okay, so this is 2R plus Y. I can simply say that this is 2R plus Y. Okay, now what is the final output Y then? Dear, final output Y is equal to 3R coming from here. Okay, and plus 1 by S times, okay, 2R plus Y. 1 by S times 2R plus Y. In this one line equation, you can get your answer. Good evening, Dreamer. Okay, in this one line equation, you can get your answer. So Y is equal to 3R plus 2 by S into R, okay, plus 1 by S into Y. Y on the left side, so Y 1 minus 1 by S can be written as 3 plus 2 by S multiplied by R. Okay, we need Y by R. So on simplification, see, S of S multiplied throughout, right side 3S plus 2, okay, and left side S minus 1, divide to the right. So 3S plus 2 upon S minus 1, 3S plus 2 upon S minus 1, option number B very simply. Okay. ठीक है जी, डन है, ऑप्शन नंबर बी इट इज. Okay, next question here. Okay, 2021 doubly 2 marks, but very simple question for 2 marks. It looks like a compensator based question, but it is actually on the very fundamentals of control system. For a closed loop system as shown in the figure, okay, 1.44 upon s, 0.1 s plus 1 is the plant transfer function. Okay, that is the plant transfer function. GCS is the compensator transfer function, which is simply 1. So there is no role of the compensator, its gain is simply 1. So GC is just given to be 1. GP is 14.4 divided by S 0.4 s plus 1. For the unit step input, what is the output response? Has damped oscillation. Okay, what is the damped natural frequency? Damped frequency is given by omega d, which is omega n root of 1 minus zeta square. That's what we need to calculate here. Quickly, let's do it up. Okay, so for omega n and zeta, we need the characteristic equation. Okay, what is going to be the characteristic equation? Let's come to the characteristic equation. 1 plus GSHS. Okay, 1 plus GSHS. What is the overall GSHS? GS into GP. What is the HS? That is equal to 1. So 1 plus GSHS equal to 0. Okay, GC का value 1 है, GP का value 14.4 divided by the S, 0.1 S plus 1. This is equal to 0. So I should be having 0.1 S square plus S plus 14.4 equal to 0. So S square, okay, multiplied by 10 throughout. Okay, so plus 10s plus 144 equal to the 0. So what should be the value of omega n? So 144 is omega n square. So very clearly omega n is 12, and this factor coefficient of s corresponds to 2 zeta omega n 12 and 2 zeta omega n is 10. Value of zeta 5 by 12. Okay, 10 by 2 cancel karte hue. Now you need the damped frequency, that will be given by omega n root over of 1 minus zeta square, and zeta will become the 25 divided by 144 zeta square. So after solving it, 144 under root 12 se cancel, it is under root of 119. Approximately what should be the value? Let's have a quick answer to this one, dear. Okay, let's have a quick answer to this one. So that should be given by root over 119, and it is 10.9 approximately. 10.9. So the very correct answer is 10.9. It's a NAT question and we have the answer, that is the 10.9. Okay, so very simple indeed for 2 marks, I would say. Let's move ahead to the next one. The damping ratio and undamped natural frequency of a closed loop system as shown in the figure, okay, are denoted by zeta and omega n respectively. What are the values of zeta and omega n? Again, a very simple question. Again, 2022 EE2 marks. Actually 2021 and 22 for EE was relatively quite easy paper. 2023 was good paper, but control system was again not that difficult in 23, also moderate conceptual, some of the questions, nothing more. Okay, so once again guys, first let me find out the gain of this inner loop actually, and then we can find out the characteristic equation. It is simply G upon 1 plus GH. Let me solve the gain of this inner loop. G divided by 1 plus G into H. H ka value 1 hai. Multiplying throughout by S. So S is divided by S plus 10. The S is divided by the S plus 10. That is the correct answer. The S is divided by the S plus 10. Okay, now what is the complete characteristic equation? What should be the complete characteristic equation? Okay, 1 plus GSHS equal to 0. 1 plus overall GS, 10S plus 10, it is cascaded with 10 by S further. 10 upon S plus 10. Further, it is cascaded with the gain, that is 10 by S. Unity feedback, it is HS equal to 1. Okay, so you know, once I solve it, this is S square, then plus the 10S plus 100 equal to 0. Your process is now actually very simple. Okay, omega n square is 100, so omega n is equal to what? That is equal to the 10. And further, 2 zeta omega n, okay, is 10. Solving that, zeta is 1 by 2. Solving the zeta is 1 by 2. Okay, so 0.5 and 10, again I'm telling you, very simple for 2 marks it is. Okay, hope you're all getting it. Let me know for any more doubts and confusions. Here it is the next question, 2021 EE2 mark. This is a good question. This one is good. Okay, so in the given figure, the plant transfer function is given to you. Okay, GP 2.2 upon 1 plus 0.1s, 1 plus 0.4s, 1 plus 1.2s, and the compensator GC is K, 1 plus ST1, 1 plus ST2. Right. The external disturbance input is DS. It is desired that when the disturbance is unit step, the steady state error should not exceed 0.1. The steady state error should not exceed 0.1. What is the minimum value of k to achieve this condition? The disturbance. Now, of course, when you are finding the error or output, whatever, whenever you are finding with respect to disturbance input, the actual input, okay, we'll consider to be null. We'll take it to be 0. We find the effect due to only the disturbance input. Okay, only due to the disturbance input. Okay, so we will consider R as 0. Okay, so if this part is 0, so you can just eliminate this summing point, but this summing point has a minus, so that minus can be adjusted here. Okay, that minus can be adjusted here, and the gain can be written as GCS. And we are looking, we are looking for this error signal. Now forget it. Chalo, let me find out this error signal actually. No problem. Well, we'll substitute. This is the error signal. Okay, so let it be like this only. So what is the value of this error signal? Very clearly, I think, is it GS? That is CS. Okay, that's a typo error here. That can be a typo error here. This part is the CS. So what is the value of the error signal? Okay, the value of the error signal is R minus C, and that is equal to minus C since we are taking R equal to the 0. Okay, now what comes here? Okay, this is the disturbance input D added with E into G, E into GC. Okay, further the output C is, okay, GP into D plus E GC. Okay, but what we need is the error signal. So error is minus C. So we can replace in terms of that. Error is equal to minus C. So C की जगह रख देंगे minus E. Okay, it is GPD plus E GPGC. Okay, bring all the error terms on one side. So error 1 plus GPGC is the minus GPD, right? Minus GPD. Okay, so what is the value of the error signal? Minus GPD upon 1 plus GPGC. Right? Okay, ji. Chalo, so let's move ahead. Now let's substitute the value of GP, GP and all these things. Disturbance will be unit step. So disturbance will be 1 by S. Okay, we are dealing in terms of S domain. So disturbance will be 1 by S. The error signal will be, substitute the value of GP, which is 2.2 upon something. Okay, so minus 2.2 upon, there are three factors, बाद में लेते हैं, into disturbance 1 by S, whole divided by the 1 plus GPGC. Okay, 1 plus GPGC, GP is again 2.2 divided by, okay, and then multiplied by GC, and what is the value of GC? K into 1 plus ST1 divided by 1 plus ST2. Now multiplying by all these three terms, okay, okay, now let me write down the expression. Okay, so we have, at the same time, what is the steady state error? Let's try to do minimum calculation, and let us limit S tending to 0, S into ES, final value theorem, according to final value theorem. Okay, so that is limit S tending to 0, S, okay, into this factor, I'm multiplying by these three brackets, so into 2.2 divided by S, whole divided by, now let us write down these factors. Ye factors ka value kya hai? 1 plus 0.1 S, 1 plus 0.4 S. Into 1 plus 1.2 S. Right, plus 2.2, right, into K 1 plus ST1 divide by 1 plus ST2. Okay. This is what I have multiplied by these three terms so as to cancel in the numerator denominator. Now, actually, S tending to 0, since you are putting the S tending to 0, okay, so all these S will get cancelled. S tending to 0, okay, S is 0, this S0, this S0, all the S put 0, all the S put 0. So eventually what I am going to get is a simple expression. It looks like complicated, but you know, when you put it, when you come hands on and put it, you are only getting the value 2.2. I think there was a minus as well. Okay, so minus 2.2 divided by, see, denominator 1 into 1 into 1 plus just 2.2K. Okay, so it is minus 2.2 upon 1 plus 2.2k. Now what is given to you? What is given to you? What is the value of k? What is the minimum value of k so that the steady state error should not exceed 0.01? Okay, steady state error should not exceed 0.01 or 0.01? 0.1. Should not exceed 0.1. Matlab it should be less than equal to 0.1. Okay. Minus 2.2 divided by what? Divided by 1 plus 2.2k should be less than equal to 0.1. So 1 plus 2.2k is greater than equal to, this is on the right side, and minus 2.2 upon 0.1 will be minus 22, yeah. Okay, divided by 0.1. Okay, so 2.2k greater than equal to minus 23. K is greater than equal to how much? Look at 10.45. K is greater than equal to minus 10.45. So what is the minimum value of K? Minus of 10.45. Okay, minus of 10.45. Dekho, there is a fundamental problem here with this question. Okay, now K is minus 10.45. Okay, which is negative. Okay, which is negative. Okay, now this is a problem because K is the gain of the compensator. Okay, of a compensator, be it lead compensator or lag compensator, it cannot be negative, otherwise the whole role of compensator to stabilize the system will be lost. Okay, so what we have to do is, there is some little bit misconcept with the question, some wrong statement. The steady state error should not exceed 0.01. Actually, I think they want to specify that the absolute steady state error should not exceed this value. So take modulus of ESS less than equal to 0.1. See, steady state error may be negative also, doesn't matter, but here let's work it out on the absolute value. Okay, absolute value. So when I take the absolute value, what is going to happen is this minus sign will be eliminated. 2.2 upon 1 plus 2.2k will be less than equal to 0.1, because once you take the modulus, okay, minus goes away. So I can now write down that 1 plus 2.2k on the other side. Okay, that will be towards lesser than side. Okay, sorry, greater than side. Okay, greater than equal to 22. Okay, so what is the value of k solving from here? Okay, 21 divided by the 2.2, and that is 9.55. What is the minimum value of k? The minimum value of k, dear, 9.55 can be taken. The minimum value of k is the 9.55. Clear? The minimum value of k 9.55. ठीक है जी. The minimum value of k is 9.55. हाँ जी, done है. So let's take that as the answer. Next question, dear. 2023 1 mark simple question. Consider a unity gain negative feedback consisting of the plant GS given below. This is the plant GS. And a proportional integral PI controller. Let the proportional gain and the integral gain be 3 and 1 respectively. Okay, so if I want to talk about the PI controller, okay, what is the gain of the controller? GCS, plant gain to given hai. Okay, and that is how much? That is generally taken as Kp plus Ki by S. Now they have given the proportional gain, suppose is 3 and the integral gain is 1. Okay, so 3 plus 1 by S, Kp plus Ki by S, they have given the proportional and the integral gain. Okay, now we know that this is going to be cascaded with this plant. Where are the PI controller? It's a feed forward controller, forward path compensator or controller, we can say. Okay, now for the unit step reference, what is the final value of the controller output and the plant output? Achha. You need the controller output as well as the plant output. Again, assuming to be a prototype unity feedback system. This is where I have the compensator gain. Okay, that is the PI controller, 3 plus 1 by S. Okay, the actuating signal is supplied to the controller. Then the output of the controller is fed to the plant transfer function, and plant transfer function is 1 upon S minus 1. That is the plant transfer function. This produces the final output, and that is also connected in unity negative feedback. This is the input signal. Okay. Now for a unit step reference input, what is the final value of controller output and plant output? Plant output means, देखो ये यहाँ पे लिख देते हैं, let this be W, let this be W. So this is what? This is the controller output. Okay, and this C actually is the plant output only. Is the plant output. So what you know, you can calculate first C with respect to R. Okay, what is the C by R? What should be the C by R here? Okay, what should be the C by R? Dear, what should be C by R? Regular transfer function, forward path gain, G upon 1 plus GH. Okay, what is the overall forward path gain? Okay, 3 plus 1 by S whole multiplied by 1 upon S minus 1. G divided by 1 plus GH. Okay, so multiplying throughout by S minus 1, I should be getting 3S plus 1. Okay, S minus 1 से multiply करेंगे तो S square then minus S. Okay, here plus 3S plus 1. Okay, simplifying it, I should be getting 3S plus 1 divided by S square plus 2S plus 1. Hanji, S square plus 2S plus 1. That is the C by R. Okay. Now they are asking the final value. That means again final value theorem should come into the picture. Again the final value theorem should come into the picture. So what is the value of C? It is R. Okay. Multiplied by the transfer function, that is 3S plus 1 upon S square plus 2S plus 1. Okay. Now the final value. R ka value 1 by S because unit step input is given to you. Final value. Okay, CSS, steady state value. Final value means steady state value. Okay, it is given by final value theorem directly. Limit S tending to 0, S into CS. That is limit S tending to 0. S is multiplied by CS. Acha, S is multiplied by CS. CS has RS which is 1 by S now. Multiplied by 3S plus 1 upon the S square plus 2S plus 1. Put down S tending to 0. This part is cancelled and then you only get 1 upon 1. The final answer is 1. So final value of the plant output is 1. The final value of plant output is 1. Okay. Now, what is the final value of the controller output? Suppose that is W. So W is related to C. How? How is W related to C? So C is actually the output of the plant. Okay, so that is GP multiplied by the input to the plant. That is the output of the controller. That is the W. Okay, GPW. Okay, so what I can say is C is equal to the GPW. Okay, or I can say that W is equal to C divided by GP. Yeah, GP का value रख देते हैं ना. What is the value of GP? 1 upon S minus 1, I think. Yeah, it is simply 1 upon S minus 1 into W. So dear, what is the value of W? S minus 1 into C. S minus 1 into CS. Okay, so what is the final value? WSS, limit of S tending to 0, S into WS. That will be limit S tending to 0, S into WS. S into WS, and WS is S minus 1. S minus 1. Okay. S minus 1 into the CS, and CS I can again write down. CS has the 1 by S element multiplied by 3S plus 1 divided by S square plus 2S plus 1. S to S cancelled, S tending to 0, this will be minus 1. This numerator is 1, denominator is 1. So this answer is minus 1. So controller final value is minus 1, plant final value is plus 1. They are asking first controller then plant. So minus 1 and 1 respectively. Minus 1 and 1 respectively, option number D. Controller minus 1, the plant final value is 1. Okay. Now here you should basically be aware na, what is the controller output, what is the plant output. Block diagram is not given, so you should be really aware. Okay, you should be really aware about the basics of controller. Okay, where is the controller connected, what is the role of the controller, what is actuating signal, okay, and all those things. ठीक है जी? Shall move ahead to the next here. A very simple question, 2022 1 mark. The open loop transfer function of a unity negative feedback system is given to you. What is the range of K for the system to be stable? Looks like RH, but it is not even RH, because if I use the characteristic equation, 1 plus open loop transfer function 1 plus K upon S square plus 4S minus 5 equals to 0, and solving it I am getting S square plus 4S minus 5 plus K, so that is plus K minus 5 equal to 0. Do you go for RH up to second order? Not required. You can go, but not required, because the only condition for stability of second order system is that all coefficients must be of the same sign. All coefficients must be of the same sign. Okay, so 1 is already positive, 4 is already positive, so you should take k minus 5 positive. So k greater than 5 is your answer. Option number C. What else to think? Simple one. What else to think? Nothing else. Done hai? Option number C. K greater than 5. Done hai? Chalo. Next one. Okay, before I take the next question, a small update for you. Acha, this workshop is already done. That was yesterday. But yeah, let's come to this one. This Sunday. That is the 8th of October. This Sunday. Starting 9 a.m. Okay, you have the National Scholarship Test. Yes, Byju's Exam Prep gives you a chance to get up to 90% scholarship. Yes, prove yourself, earn your respect. Okay, so based on your performance in this scholarship test, you can get as much as up to 90% scholarship onto the GATE preparation programs. Okay, so you can take a next step towards success in GATE. Okay, conquering your dream by studying under the best faculties. Okay, come to this question. Doubly 2 marks question. Very simple actually. Doubly, and that to 2023. Doubly 2 marks simple question. Come on, quickly answer this. A simple one only. Okay. Okay, so let's proceed once again, dear. So as I told you, this was a simple one only. The magnitude and phase plots of an LTI system are shown in the figure. What is the transfer function of the system? What is the transfer function of the system? Come on. Come on, everybody. What should be the transfer function of the system? Now the magnitude is 8 dB and it's a flat magnitude, means there is no pole or zero. Okay, there is only the initial part which is having the zero slope. Okay, so no poles at origin also, because if there were any other poles or zeros, there should be corner frequency. Okay, that is just constant. So this 8 corresponds to the 20 log k. The standard results of Bode plots can be used. Okay, so solving it, k will be 10 raised to the power 8 by 20. Okay, so just you have to solve this part and you should be getting it as just 2.51. Getting it as 2.51. Okay, so magnitude part is 2.51. Okay, magnitude part is 2.51. Now look into the phase part. Look into the phase part. Yeah, definitely there is a phase term. Okay, definitely there is a phase term, and that too it's a linear function. See, it's clearly linear. It's given with respect to omega. Okay, this particular phase plot directly is with respect to omega. The magnitude plot is the Bode plot with respect to log omega, but the phase plot is versus omega. And definitely if you have plotted with respect to omega, it's a linear graph, straight line. Okay, so we can write down phase is equal to okay, minus omega t. Yeah, if you want you can write it like this, minus k omega. Any constant k can be there. Okay, minus because it's a decreasing line. But there is one point omega equal to 1 where the value of phase is given. Okay, where the value of phase is given, that is minus 60 degree or minus pi by 3 actually. Okay, minus pi by 3 will be minus k into the 1. Okay, because at omega equal to 1, phase is minus pi by 3. Use the standard unit of radian. So solving it, k equal to pi by 3. Pi by 3 approximately is 1.047. So what is the transfer function then? Okay, so I've solved it here, no issues. What is the transfer function then? It is simply k, okay, or it can be written as, okay, what can be gj omega? It can be magnitude mod gj omega multiplied by e raised to the power j angle g omega, the phase part. So magnitude part is the constant 2.51, the phase part is e raised to the power, okay, e raised to the power, okay, minus k omega t, e raised to the power minus k omega, k is 1.0, e power minus j 1.047 omega. Okay, k omega, k is 1.047. Okay, e power j theta. Okay, e power j angle phi omega. So that is the answer. Okay, that is option number D. Option number D. Okay, I have written in terms of j omega domain. You can convert into S domain as well. Okay, convert it to the option number D. Simple one, very simple actually. Okay, next question. Okay, 2022 EE 1 mark, again basic analysis question. The Bode magnitude plot of a first order stable system is constant with the frequency. Okay, is constant. The Bode magnitude plot is again constant with frequency. Okay, but the asymptotic value of the high frequency phase for the system is minus 180 degree. The phase plot is given to you. Okay, but phase is this time not exactly linear. It shows some change in the slope. Okay, that means there are some polar zero terms, but there is no change in the slope of the magnitude curve. Okay, there is no change in the slope of the magnitude curve. Okay, but there is slope change in the phase curve. So definitely some poles and zeros are there. You have to identify what pole and zero. Okay, now definitely because there is no slope change in the magnitude curve, and still I am telling you there will be a pole or zero, there will be some pole or zero. It is only possible that a zero corner frequency cancels the pole corner frequency, because at every corner frequency the magnitude slope should be changing. At every corner frequency the magnitude slope should be changing. Okay, so what you should have is the pole corner frequency should cancel with the zero corner frequency. Okay, so that is why a pole and zero, okay, should be at the similar location. But if you take one LHP pole and one LHP zero, or one LHP pole and one LHP zero, now dekho, if pole and zero are at the same frequency and that too in LHP, then they cancel. Then this is cancel. Not only the corner frequency cancel. Okay, what this option mean to say that, okay, this is of the form, okay, this is of the form, okay, both are in LHP, so both is S plus A form or S plus A form. Okay, because the pole and zero should be at the same location and both should be LHP. Okay, so ye to cancel hi ho gaya. Ye to cancel ho gaya. This doesn't make a sense. Okay, we can think about the option number A. Okay, one LHP pole and one RHP zero. Okay, one LHP pole and one RHP zero. RHP 0, okay, S minus A, and LHP pole, S plus A. Why only we are choosing LHP pole? Because otherwise the system is unstable. Option also says LHP pole, but usually pole should be in LHP for stability. S minus A upon S plus A, or it could be A minus S upon A plus S. It depends what format you are taking. Okay, final phase is minus 180 degree, so minus 2 tan inverse omega. Let's go with this A minus S upon A plus S. Okay, now if I consider GS is equal to A minus S upon Gj omega, let's directly take that, Gj omega as A minus J omega divided by A plus J omega. Okay, so what is the list of corner frequencies, dear? Okay, the zero corner frequency, okay, the zero corner frequency, that will be A. The pole corner frequency, that is also equal to the A. That is also equal to the A. That is also equal to what? That is also equal to A. Okay. Chalo, omega CZ, omega CP. Okay, corner frequency of zero and pole. Both will be equal to A, because both are, you know, when you take even in the time constant form, you will get it as A. Okay. 1 plus J omega by A. Time constant is 1 by A, so corner frequency is A. Both are same. That is why, because both are same, okay, you don't get any slope change in the magnitude curve. Now, what about the phase expression for this? So, when you take the angle Gj omega, let me just tell you why this option is correct. Okay, A minus J omega, the phase is tan inverse minus omega by A. For denominator, we shall subtract, and then again it will be tan inverse omega by A. Okay, so tan inverse minus theta is minus tan inverse theta. Eventually, you will have minus 2 tan inverse omega by A. Minus 2 tan inverse omega by A. Minus 2 tan inverse omega by A. Okay, now if you put omega equal to 0, okay, the angle part is 0. Okay, if you put omega tending to infinity, high frequency, okay, the angle should be, okay, minus tan inverse infinity is 90 and 2 times it is, so that is minus 180 degree. Perfectly matching it is. Okay, it should be the perfectly matching. Okay, so minus 180 degree. Okay, so option number A is correct. Option number A is correct. Now, why I did not took C and D? Okay, 2 poles and 1 zero, whether it is LHP or RHP, forget. 2 pole and 1 zero, even if their corner frequency cancel, one of the pole or zero will be extra, na? Okay, and if there is an extra pole and zero corner frequency, there should be some slope change in the magnitude curve as well. That is why C and D will not be possible. Okay, and why B is not possible, that I told you, because S plus A upon S plus A will cancel each other. Okay, done hai ji. Next question, be ready for it. Yeah, the Bode magnitude plot for the transfer function V0 by Vi of the circuit is as shown below. What is the value of R? Okay, what is the value of R? You can call it as a network question or control question. Okay, what is the value of R? Now, Bode plot, actually, this Bode plot, the peak value is given to you. In this Bode plot, the peak value is given to you. Okay, and this peak value, okay, of the frequency response corresponds to MR. Okay, this corresponds to MR, the resonant peak. Okay, and that is given in dB actually. That is given in dB. So what is this? This is 20 log MR. 20 log MR is 26. What should be the value of MR? 10 raised to the power 26 by 20. And this will be approximately how much? Let's check out that value. Let's check out that value. It is above 0 level only. Yeah, correct. Okay. Okay, 19.95, that is approximately 20. Approximately 20. The resonant peak is given to you, that is 20. Acha, now we know resonant peak depends on what? Okay, now we know resonant peak depends on what? Okay, resonant peak depends on what? Okay, MR is given by the formula. MR is simply given by the formula 1 upon sine 2 phi, and that is given to you as 20. 20 again. So what is the value of sine 2 phi? That is known as 1 by 20. Okay, so what is the value of 2 phi? When I take the sine inverse of this value, okay, 2.86. Oh, let's take it in degree only, correct. So this is 2.86, or sine theta is positive, maybe first and second quadrant. Okay, first and second quadrant. So it could be even 180 degree minus 2.86 degree. Okay. And that is 177.14. So 2 phi is either 2.86 degree or 177.14 degree. Okay, so what should be the value for phi? If you take the value of phi, it will be 1.43 degree, or it will be equal to how much? 80. Okay, 8.57. Okay, but for resonant peak to exist, okay, for resonant peak to exist, we know zeta, which is cos phi, okay, is less than 1 by root 2. The condition is zeta less than 1 by root 2, and that is only possible if phi is greater than 45 degree. You must have studied this, you know, zeta and MR and omega R condition. Okay, so MR, okay, for MR to exist, zeta should be less than equal to 1 by root 2. The phi should be greater than 45 degree. So what is the phi that you are going to take? 88.57. Okay, so correspondingly, what is the zeta? Zeta is cosine of this value, and if you take the cosine of this value, 0.0249, approximately 0.025. Okay. Okay. Right. Chalo. That's hidden behind the derivation Venkatram. So you can watch my session on the Bode plots of frequency response. You will get it there, because if I go into that, I think 10-15 minutes minimum it will take. Okay, 10-15 minutes minimum it will take. So you can watch my complete sessions, because some more questions to be discussed right now. Done it. Okay, even if I go very briefly, it will take 10 minutes or so, you know, because we need to go into derivation to understand why zeta less than 1 by root 2 comes. ठीक है, आ जाते हैं यहाँ पे. So now that zeta we know is related with the values of the RLC of the circuit. Okay, now it is a 1 mark. They are expecting the basic results. Okay, what is the characteristic equation you can take here? S square LC plus SRC plus 1 equal to 0. That is the basic characteristic equation of the series RLC circuit. Okay, or you can take it S square, okay, divide by LC, okay, divide by the LC, so you get R by L into S plus 1 by LC equal to 0. Let's pick up from here. Okay, so we have S square LC plus R by L into S plus 1 by LC equal to 0. Okay, where some of the values are given, R is missing, but L and C is given to you. Okay, the L and C is given to you. Okay, cool. Okay, so we have the value of omega n square, that is 1 by LC, and that is 1 by LC. L is millihenry, 1 millihenry, 10 power minus 3, and capacitance is 250 microfarad. It is given by the 250 microfarad, 10 raised to the power minus 6. Okay, 10 raised to the power minus 6. So this is 1 upon 25, and 10 power minus 9 and 10 power se cancel karke 10 power minus 8. So I should be getting omega n as under root of this, that is 1 by 5, 10 power minus 4. Okay, or basically 10 power 4 divided by 5, that is 2, and then 2000. Omega n is 2000. Okay, just keep checking the calculation. And now let's come up here to zeta omega n is R by L. Okay, so what is the value of R? R is equal to 2 zeta omega n multiplied by L. Zeta as obtained by the peak, resonant peak 0.025, multiply by omega n, that is 2000, multiplied by n, which is 1 millihenry, 10 power minus 3. Okay, so how much is this value turning out to be? 25 into 250 into 200, 100 into 10 power minus 3. So 10 power minus 1, 0.1 ohm. The R should be 0.1 ohm, just check out the values. The resistance should be 0.1 ohms, just check out the values. 0.1 ohms. Done hai ji? Alright, so let's move ahead to the next question then. Okay, conceptual one from the Nyquist plot. In the Nyquist plot of the open loop transfer function GSHS equal to 3s plus 5 upon s minus 1 corresponding to the feedback loop shown in the figure, the infinite semicircular arc of the Nyquist contour in the S-plane is mapped into a point at. Okay, corresponding to the loop given to you. Okay, open loop transfer function GSHS is given corresponding to the feedback loop. Okay, now what is this GSHS? 3s plus 5 upon s plus 1. But the infinite semicircular arc of the Nyquist contour in the S-plane. Okay, for this it is expected that you have studied what Nyquist plots are in detail, and you know how Nyquist contours are considered. What is the meaning of this infinite arc? Okay, what is the meaning of this infinite arc? So if I take this, okay, maybe this particular semicircular infinite arc of the Nyquist contour they are talking about. And if you consider any point in this contour, okay, if you consider any point in this contour S, it can be broken as R e power j theta. But since it is semi-infinite, let me join it here. Okay, so when you break a complex number into R e power j theta, the theta is the phase part which is measured with respect to the positive x-axis, and R is the magnitude. Okay, but since this is the infinite, semi-infinite arc, okay, semicircular infinite arc, okay, S is equal to R e power j theta, but R is tending to the infinity. Okay, R is tending to infinity, eventually S is also tending to infinity. You can directly put down the value of S tending to infinity there. Okay, so what should be the value of limit S tending to infinity GSHS? What they are asking? Okay, the transfer function, open loop transfer function GSHS corresponding to this infinite semicircular arc is mapped to what point? It is mapped to what point? Calculate this value. Okay, corresponding to this semicircular infinite arc, S tends to infinity. So limit S tends to infinity GSHS, which is 3s plus 5 divided by the s minus 1. Okay, even if you solve it by the L'Hospital rule, because it is infinity by infinity form, okay, if you solve it by the L'Hospital rule, you get 3 by 1, that is 3. Differentiating both numerator and denominator. The answer should be 3. Correct answer is the C. Okay, ji, the very correct answer is the C. The very correct answer is C here. Done hai ji. Let's move ahead to the next question. Yeah, correct one Chinmoy, correct one Harihar. Okay, next one. Again, 2022, 2 marks conceptual. It's not 2 marks. It's not going to be very lengthy, but it's purely a conceptual question, right? For the infinite arc of the Nyquist plot. Okay, Venkat, it's not the infinite plot. They are mentioning that the infinite arc of the Nyquist contour. Okay, and because it is infinite arc, okay, S can be tending to infinity. Actually, R tends to infinity, so eventually S tends to infinity. So calculations you can use S tending to infinity. Whatever may be GSHS given, that is correct. But when you are evaluating, when you are going to mark the GSHS on the Nyquist plot corresponding to the semicircular infinite arc, s tending to infinity can be kept. Correct hai ji Venkat. Okay ji, so the open loop transfer function of a unity gain negative feedback system is given to you, gs equal to 1 by s plus 1. Okay, the Nyquist contour in the s plane encloses the entire right half plane and a small neighborhood around the origin. Entire right half plane and a small neighborhood around the origin. Okay, in the left half plane. Usually we take it in the right half plane, but they have defined a Nyquist contour, okay, such that this small portion around the origin, we don't take origin because otherwise s tending, whenever a function directly has a pole at s equal to 0 like this, okay, the GSHS will become undefined. Okay, so that is why we usually never take the Nyquist plot crossing through origin. We usually take it from right half plane for the stability point of view, we know, but here they have taken it from the left half plane. Okay, now the number of encirclements of the point -1 plus j0 by the Nyquist plot corresponding to the Nyquist contour is denoted as n. What is the value of n? What is the value of n? What is the formula you use for the n? What is the formula you are going to use for the n? Okay, n is given by p plus minus z plus. N is p minus z. Okay, please look into that the Nyquist plot that is given, the Nyquist path that is given is itself clockwise in nature. So that is clockwise Nyquist contour. And whenever it is the clockwise Nyquist contour, we will use the formula p minus z. If it is by chance anti-clockwise contour, you will be using the z minus p formula. Okay, you will be using the z minus p formula. Okay, now n is the encirclements of, okay, a quick recap to understand this. N is what is the encirclements of -1, 0. Okay, Z is what is the zeros of. Z is what is the zeros of what? It will be the zeros of the characteristic equation, that is 1 plus GSHS. This will be representing the zeros of 1 plus GSHS, okay, in the Nyquist contour. Okay, that is usually the RHP, but let me be very clear in the definition that, okay, this will be the zeros of 1 plus GSHS in the Nyquist contour, and then we all know what is P plus is the poles of open loop transfer function directly. Okay, this is going to represent the poles of open loop transfer function, that is the poles of GSHS. Okay, that is the poles of GSHS, okay, within the Nyquist contour. The poles of GSHS within the Nyquist contour, correct? Within the Nyquist contour. Now look into this Nyquist contour. These are the poles of GSHS given to me. Okay, directly also you can calculate what are the poles of this transfer function are representing 0 and -1. Okay, that is the 0 and -1. Okay, out of which, because I have taken the Nyquist contour slightly to pass through the left half plane, slightly to pass through the left half plane, so there is by chance a pole which is enclosed. There is by chance a pole which is enclosed, and hence I can take the value of P which is equal to 1. There is an enclosure of one particular pole. Okay, now since I need the value of n, what is the value of z? Okay, so I'll be going to the characteristic equation here, and the characteristic equation will be briefed as 1 plus 1 by s plus 1, okay, equal to the 0. S square plus s plus 1 equal to 0, and all the coefficients are positive, positive, positive. Because it is second order, we need not go to the Raut-Hurwitz criteria. All the coefficients are positive. Okay, all the roots will be in the left half plane. Okay, z is equal to 0, and now we are into the answer. N is equal to p minus z. Okay, n is equal to p, which is 1, z is 0, so answer for n, that's going to be 1. Really a good conceptual question. To be very honest, it's a good conceptual question. Okay, it's a good conceptual question to be discussed up, right? Okay ji, it's a good conceptual question. Done hai. Right? Chalo, let's move ahead to the next. Let us move ahead to the next. Yeah, let's come here. Have a look into this. A question based on state space description. Just a second. Chalo. So consider the state space description of the LTI system with the matrices ABCD mentioned for the input sine omega t, omega greater than 0. Okay, the value of omega for which the steady state output of the system will be 0. Now we are looking for the steady state output for a sinusoidal input. Okay, and hence I should be targeting the transfer function. What I can do here is, I can write down x dot is equal to ax. Let me write down the model actually. That is 0, 1, minus 1, minus 2. X dot is equal to ax plus bu. Okay, y is equal to cx. Okay, that is 3 minus 2. Okay, plus du. Okay, d is given to you as 1 plus du. Okay, now this question only becomes easily solvable if you remember what the standard models are. Otherwise you're going to waste a lot of time, and that cannot be acceptable in the exam hall. This is nothing but your CCF model. You can look into this matrix and try to identify 0, 1, minus a0, minus a1. Okay, that is the CCF model, controllable canonical form. Okay, and if you identify that it is controllable canonical form, the transfer function y by u will be obtained as, so now what is this? This is C0 and C1. C0 means the constant term and C1 means the coefficient of S. Okay, and what is the B value? This is the B value, and that is the common in the numerator, which is simply 1 whole divided by, okay, now S square. This is the constant term of the denominator with opposite sign. So 1, go reverse. This should be plus 2S opposite sign plus S square. 1 plus 2S plus S square. Okay, plus the D. Okay, and the D is 1. Plus the D is 1. If there is no D, we write down only this transfer function. Okay, so what is the y by u? Now let's try to simplify this. Okay, what is the final transfer function? You are getting y by u. Okay, the final transfer function y by u. Perfect. Yeah. Okay, so let's call this transfer function. Okay, suppose you have the transfer function ts. Okay, as y by u. Let's try to simplify this part. So that is 3 minus 2s is divided by s square plus 2s plus 1 plus 1. On simplifying this, I should be getting a s square in the numerator as well. Then plus 2s minus 2s got cancelled, right? And then plus 1 and plus 3. That will be plus 4. S square plus 4 upon s square plus 2s plus 1. Converting into frequency domain, since the input is sinusoidal, so it is necessary to convert your transfer function into the frequency domain. So if I put s equal to j omega, this will become 4 minus omega square because j square is minus 1. Then this will be the 1 minus omega square. Okay, plus 2s, so s equal to j omega, so plus j 2 omega. Plus j 2 omega. Done? Okay, done. Okay, now for the input sine omega t, what is the value of omega for which the steady state output? Okay, so dear, whenever the input is sinusoidal, sine omega t, okay, what is the output you are expecting? The output for the sinusoidal input is given by modulus of tj omega. The amplitude is multiplied by modulus of tj omega, and there will be a phase shift, that is sine omega t plus angle tj omega. Okay, but you need the output to be 0. The output will be 0. That means the magnitude term itself should be 0. Okay, and to even separately calculate the magnitude, it is very clearly seen that if you put omega equal to 2, the whole function, see, whose magnitude is 0? If the magnitude of a complex number is 0, that number itself is 0, na? Magnitude means the point lies at the origin. So very simple, you can state from here that omega square equal to 4 will be required, and hence omega equal to 2. Omega equal to 2. Okay, omega plus minus 2 mat likhna because they have mentioned positive frequency. So omega equal to the 2. Right, everybody? Omega equal to 2. Now this uses two concepts. One is the sinusoidal response, the steady state response of a system to sinusoidal input, and number 2 is the CCF model. Otherwise, if you calculate the transfer function by what model? Okay, C phi s b plus d. That is the general formula to calculate the transfer function of the system, but eventually you're going to spend a lot of time using this. First you will calculate state transition matrix and all those calculations will come up, right? Moving ahead to the next question here. Okay, this is a similar question. I want to go to the steady state question. That is same sinusoidal question. So this question is same sinusoidal response. Okay, sinusoidal response. So I shall give you one question as homework. Okay, since time is also approaching 10:30. Okay, this one question, kindly take it as homework. Just one you can manage. If any doubts, please ask me in the telegram. And ask me in the telegram, no doubt. Okay. Yeah. Because it is again on the sinusoidal response. Okay, the input output relation will be the same. This one was a decent question on state space description that we have used. Let's come here, another good question. It's simple only, but you need to know different varieties. 2021 EE2 marks that state space representation of a first order system is given to you. Okay, since it is a first order system, okay, that means only one state variable. Number of state variables corresponds to the order of the system, so there is only one state variable. Okay, and suppose that is one state variable, suppose that is the x1. So whatever is this equation given, na dear, okay, you can write this as x1 dot actually is minus x1 plus u. Okay, and y is equal to x1. Now let's try to convert this into the graph. Okay, x is the state variable, u is the control input, y is the controlled output. Okay, y is the control output. Yeah, if you want, leave it in terms of x also, that doesn't matter. There is one state variable that you must be knowing, and that is x. Okay, that is x. Okay, now let u equal to minus kx be the control law, where k is the controller. Again, we are introducing the controller in the state space model. Okay, what should be the value of the k to have a closed loop pole at minus 2? Okay, now in order to have the knowledge about closed loop pole, I need to have the transfer function. To have the transfer function, okay, let's try to sketch the signal flow graph, because I don't only want the transfer function of this, I want to introduce a control law u equal to minus kx. Okay, so have a look into this. X dot is equal to minus x plus u, and y is equal to the x. Y is equal to the x. Okay, so we know that since it is a first order system, it will be employing only a single integrator. Integrator gain is given by 1 by s, and the output of integrator is taken as the state variable. So its input will be the x dot. Okay, now x dot is minus x plus u. Okay, minus x plus u. So we can define the input node here. Okay, and get it connected here. So plus u is coming, but it also has minus x. So there is a loop coming up. There is a feedback path coming up with the gain minus 1. So that now this x dot is clearly minus x plus u. There are the two incoming paths. Minus x plus u. And y is equal to the x. Y is equal to what? Y is equal to the x. Okay. Now this is the original graph. Okay. But now I want to introduce u equal to minus kx as the control law. Okay. That is u equal to minus kx. U also will be minus kx. So let me add up this additional graph here. Okay, minus kx. So I take a branch from x, multiply it with gain minus k, and then I can say that u is equal to minus kx. Okay, now for this modified signal flow graph, what is going to be the transfer function? Okay, now what is y by u for this modified signal flow graph? Okay, look into directly Mason's gain formula. How many forward paths? Clearly there is only one forward path. Okay, there is only one forward path. I am just using P1 del 1 divided by 1 minus sum of loop gains. Okay, let me see how many loops are there. But there is definitely only one forward path, okay, from the input to the output, and whose gain is simply 1 by s. These two are unity. What is the path factor? Path factor. So if I erase the first forward path, if I am going to erase the first forward path, what is left? If I erase the first forward path, all the loops are open, and if a graph doesn't have a loop, its determinant is 1. So the path factor is accordingly 1 divided by 1 minus loop gains. Now you have one loop L1, okay, that is 1 by s into minus 1. So minus 1 by s. Okay, now take this. This is also another loop, 1 into 1 by s into minus k. Okay, let's call this as loop number 2. Okay, and loop 2, 1 by s into minus k, that is minus k by s. Okay, L1 and L2. There are two loops. And actually both of them are using this branch. Both of them are touching. Because both the loops are touching, so you need not consider their product. Okay, we consider the product only for non-touching loop pairs. Okay, so eventually the y by u is turning out to be multiplying throughout by s. 1 divided by s, here minus minus will be just plus, okay, plus 1 plus k. So what is the pole? The pole is coming up at minus 1 plus k, and we need the pole at minus 2. Okay, so 1 plus k will be 2. What was the question? The controller is so introduced that we get a closed loop pole at minus 2. So equating with the given condition, I got my answer k equal to 1. 2021 EE2 marks. Good question. The value of k will be 1. Perfect. The value of k will be equal to the 1. value of k will be equal to 1. Done hai ji. All right dear. So this is going to be the password for today's PDF. As you know, you'll be getting my PDFs which are password protected. Okay, because those who watch the session, they only need the benefit of the PDF. So the PDF password will be everything small state, STATE, state. Use this password to access my PDF. Okay, and yes, for the those who have started late, yeah, those who need a quick revision of the GATE syllabus, the GATE 2024 crash course now available for all of you with the complete syllabus coverage, but in the remaining limited time. Okay, but in the full complete syllabus, fast track theory revision plus lot of question practice to make you perfect, with live classes, recorded lectures also available, study material, mock test, practice quizzes, everything will be available. Okay, for all the branches, ECEE and everywhere. So study with your best faculty team and 666. Done hai ji. Okay, I'll just share you my Telegram link here. Okay, where are you going to get that PDF? I'll just share you that link. Just a second. Okay ji, that's it from my side. Bye bye. Good night. Stay safe and take care of yourself.